So the penultimate set of questions using bond energies to get delta H. So first thing we must always do is draw out the structures. Okay, so we got ethene there, C2H4. We got 3 O2s, so that's 3 O double bond O's. On the right hand side we got 2 CO2s and 2 H2Os. Okay, now delta H, which is minus 1387 in this particular reaction here, is where we add up all the bond energies broken, and that's a positive number. We add up all the energies made, and that's a negative number, and then we put them together. So it's effectively bond energies broken minus bond energies made. So let's see what we've done. We've broken carbon-carbon double bond that's worth 614. We've broken oxygen-oxygen double bond, which is worth 495, excuse me, but we got 3 of them. We've broken 4 CH bonds, but we don't know what those are. That's X. That's what the question was. Use those blah, 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 blah to get the average bond enthalpy of CH. So there we are. CH is X there. Okay, and we got 4 of those. Put all that together, and the total energy made, 2099 plus 4X. Let's go over to the made side. We made some C double bond O's, which is 799. We made 4 of those. We also made some OHs, which are worth 465. And again, we made 1, 2, 3, 4 of those. So put all that together after adding it up, and total of 5056 kilojoules from the making. Now, delta H minus 1387 is then green, the stuff broken, minus red, the stuff made. Rearrange that, we get 4x is 1570, or x in this case 392.5 kilojoules per mole, should give it to 3 significant figures because that's what we got here. So 393 would be the proper answer. 18, we need delta H for this reaction. So again, let's look at what we've done. CO, carbon monoxide, has a triple bond. Unfortunately, the level that you study Lewis structures does not enable you to know why it's a triple bond. We talked about why it's a triple bond in the Molecular Structures 1 module. It's a triple bond. That's why it's so big, okay? Carbon-oxygen double bond is actually, what was it, nearly 700. Carbon-oxygen triple bond is 1077. I wrote this vile, disgusting fallacy here, CO double bond, because that's what the A-level says. We know it's a triple bond. So anyway, we're going to be breaking one of those, and 2 HH bonds for the 2H2, and of course then we're making methanol right here. What do we break? Carbon-oxygen triple bond, 1077. 2 of those hydrogen-hydrogen bonds, so total broken, 1949. Making, let's see what we've made. Well, we make a carbon-oxygen bond right there. That's worth 336. We make carbon-hydrogen, 1, 2, 3 of those, so 3 times 413. And we make an OH bond that's 464. Add those up, and we get 2039. So delta H is this, what has to be put into break, minus this, what comes back out as you make 1949 minus 2039, or minus 90 kilojoules per mole. Why is the calculated value might not be the same as the literature value? Well, the literature value would be where you actually measure it. The calculated value, we used average values for these. Okay, and when you go from one molecule to another, this CH bond might not be the same as the CH bond in another molecule because this carbon's got an oxygen attached to it. So different atomic environments, right, for the carbons in this case, or the oxygens, or even the hydrogens, will change the value of the bond energy. Not hugely, but enough. So therefore our bond energies, which are just average values, don't necessarily relate to the actual bond energy in any of our molecules here. Except, of course, the carbon-oxygen triple bond in carbon monoxide, because we know exactly what that is. But this OH might be different from, say, an OH where the O is bonded to another H, or where the O is bonded to a phosphorus, and so on, and so on, and so on. Right, so again, we want to calculate the average bond energy for a CH using ethane, combustion of ethane. Now, nasty people haven't even told us what the equation is, so let's do that. Ethane, C2H6, combustion, O2 makes CO2 and H2O. We need 2 carbons, so 2 CO2s, we got 6 hydrogens, so 3 H2O. Balance out the oxygens, we got 7 oxygens. We know that our reaction is a combustion, a standard combustion, so that's 1 ethane, which means that we have to have 7 halves or 3.5 oxygens to balance out the oxygens. Okay, so we balance the equation. Now let's draw out the structures. There's ethane. We've got total of 3.5 O2s. Well, I'm not going to try and draw half of an O double bond, so we'll just say it's this bond times 3.5. On the other side, we've got 2 carbon dioxides, and we got 3 waters. So breaking bonds, we've got a carbon-carbon bond will break. We got oxygen-oxygen bonds. 495 is their energy times 3.5, and then we've got X, the carbon-hydrogen bond. That's what we're asked for. We have 6 of those. So we add all those up and we get 6x plus 2080.5. Making, we've got CO double bonds, 799. We got 1, 2 times 2 is 4 of those. In the waters, we've got OH bonds. There's 2 in each water. We got 3 waters, so that's a total of 6 of those bonds. So thus 5974. We're told delta H is minus 1561. And that equals the breaking minus the making. So that's the broken, that's the made. Put all those together. 6x is 2332.5. X in this case 389 kilojoules per mole. So a different value for the carbon hydrogen in this because it's different molecules using different averaged bonds, different bonds associated with it. Okay. So average bond enthalpy, CC bond quotes 348 kilojoules per mole. What's meant by bond enthalpy? Well, it's the energy required to break 1 mole of bonds. Now, you also have in the definition or to make 1 mole of bonds. No, it's not to make 1 mole of bonds. To make 1 mole of bonds would be minus 348. So you need to be precise there, right? Bond energy, because it's a positive number that's given, it's the energy required to break 1 mole of the bonds. So rather now long second part, that's ethane. We've got that again, reacts with hydrogen in a similar way to ethene. So adds across the double bond and we make ethane. So we want to now get that energy change. So let's draw out the structures. There's the structure of ethane, 2 hydrogens. And then over here we have ethane. Broken, well, we break a carbon-carbon triple bond. We break 2 carbon-hydrogen bonds. And we break 2 HH bonds. So put all together, we broken. Now notice I'm breaking all of the bonds here. It just makes it a little bit easier. Then over here for making, we make a carbon-carbon bond and we make 6 carbon-hydrogen bonds. Now notice I could have said, well, I don't actually break these carbon-hydrogen bonds here because they're still there. So what I could have done was just exclude carbon-hydrogen from here and then exclude 2 of those carbon-hydrogens from there. However, it becomes easy to lose track of your bonds. So thus, especially under exam conditions, break everything and make everything from scratch. So add those up, 2826, delta H is going to be the 2537 energy needed to break, minus 2826, the energy getting back out to make, so delta H is minus 289 kilojoules per mole. Final topic, lattice energies. Hope you can see these numbers well enough. Give the value for the standard enthalpy change of atomization of chlorine. So let's look throughout all this and see what happens. Well, here you're getting solid calcium and gaseous chlorine going to solid calcium chloride, so we're not vaporizing anything there. Here we're vaporizing the calcium, going from solid to gas. Here we're ionizing the calcium, going from Ca2 plus, or Ca to Ca2 plus, but all the way through here it's Cl2 gas, Cl2 gas, Cl2 gas. Up here we go from Cl2 gas to 2Cl gas. So there is Cl2 gas going to 2Cl gas. That's what this energy change at 242 corresponds to. But we wanted the energy change of atomization of chlorine. That implies 1 chlorine. So therefore, half of that at 121 kilojoules per mole. Calculate standard enthalpy of lattice formation of CaCl2. Well, lattice formation is where you go from the gaseous ions to the ionic compound in the solid state. So this here is the lattice energy, right? Enthalpy of lattice formation. So going straight from there to there is the lattice energy, or we can just go in this little cycle all the way around, okay, as shown by my nasty little red hand-drawn arrow there. So lattice energy going straight is equal to, going backwards here, so minus 728, minus 242, minus 1735, minus 178, minus 795, okay, because every time we go in reverse we change the sign. Here we're going in the sign for the negative side. This is minus 795 going here, okay. Pop it all in there. Lattice energy minus 2222 kilojoules per mole. And finally, a student incorrectly states the second ionization of calcium is 1735, as this is the energy needed to make Ca2+. So indeed, this here goes from Ca to Ca2+. Okay. Trouble is, though, that's actually two ionization energies, because ionization energies, the first one is when you strip off one electron, and the second one here is where you take just the second electron. So in other words, the second ionization energy isn't 1735, it's the first plus the second is 1735. Okay, but second ionization energy is always bigger than the first. So in other words, you can't just divide this by 2 and say, well, half of it's the first and half of it's the second. So therefore, the second ionization energy has got to be bigger than this over 2. And now you can just sort of throw some numbers around, say between some 900, that's what that is, about 860. So between about 900 and 1500, because you have to have a little bit of energy for the first ionization energy. Hope that this was amusing, educational, and didn't detract from what you've already learned in class for answering A-level questions.